Right, so when we talk about rational exponents, we mean a variable raised to a fraction. Your numerator is going to be your exponent. Your denominator is going to be your index, the thing that tells you whether it's a square root or a cube root. So for instance, if you had 8 to the 2/3, the numerator 2 is your exponent. The denominator 3 is your index. So that will be the thing that tells you if it's a square root, cube root, in this case, cube root. There is not an order of operations for these radicals. So you can take the cube root first and then raise it to its exponent of 2, or you can square it first and then take the cube root. So for instance, if we take the cube root of 8, we'll get 2, and then 2 squared is 4. If we take 8 and square it, that's 64, and the cube root of 64 is also 4. But more often, this is a faster, easier process to do the root first. So when we see x to the 5/4, that literally means the fourth root of x to the 5th. So what's going to get rid of the fourth root? Raising it to the 4th power. What's going to get rid of raising it to the 5th power? Taking the 5th root. And so another way that we could express that would be to raise it to the 4/5, because again, that's taking it to the 4th power, and that's taking the 5th root of it. You'll also notice that a power raised to a power, when you multiply, gives you 1. So we'll have plain x on the left-hand side as we want it. Now, what you do to one side, you have to do to the other side. So here we'll have 32. The exponent will be my numerator, and the index will be my denominator. Now, I really don't want to take 32 to the 4th power, so instead I'll take the 5th root of 32 first and get 2, and then I can raise 2 to the 4th power and get 16. So that's much simpler than the other. Look at another one of those. If I have x plus 5 to the 3/2, I could raise that to the 2/3, because again, this is cubing it and taking the square root. This is squaring it and taking the cube root. So they will undo each other. A power raised to a power gets multiplied, and that would just be 1. So we want to raise it to its reciprocal. All right, on the opposite side, what we do to one side, we do to the other. So the exponent will be 2, and the index will be 3. And so this is the same thing we were working with up here just a moment ago. Whichever of these two methods you like better is going to give you 4. So now to get x by itself, let's subtract 5 from both sides, and we'll get x is equal to a -1. If instead of writing the equation with a rational exponent, if instead we wrote it with the radical in it, to solve that, we want to get the radical alone on one side by itself. In order to get rid of that square root, we're going to need to square both sides. So you can imagine if this x were over here and I squared it, I would have to FOIL out with that radical. So it's so much simpler if I can get the radical alone on one side and everything else on the other side. So when we square both sides, the square root and the square cancel each other out, and now we're left with a quadratic. So for your quadratic, let's move it all over to one side set equal to 0. So I'm going to subtract the 3x, and I'm going to subtract the 18. And then you can solve that by factoring, by completing the square, quadratic formula, this one factored. So once we factor, we can set each of those factors equal to 0. Now something that we need to be careful of is picking up an extraneous root. The key to extraneous, the root word there, is extra. An extraneous root is an extra solution that you pick up. You didn't do anything wrong. You solved correctly algebraically, but anytime you multiply both sides of an equation by a variable that was not there originally, you run the risk of picking up an extraneous root. And you'll notice that we squared this side. In essence, we said take x and multiply it times another x. So we've multiplied by a variable that was not there originally. The only way to check to see whether you have an extraneous root or a true solution is to plug back into the original equation, the one that you used before you squared it or altered it in any way. And so you'll notice when I take 6 and plug it back in, I do get a true solution. But when I take -3 and plug it back in, I do not get a true statement. And so -3 is an extraneous root. I would not list it as a solution to my problem. All right, look at another one of those. We want to isolate the radical on one side by itself, and then we're going to square both sides to eliminate that radical. So the square root and the square cancel each other out. Now, on the right-hand side, 3x minus 1 squared literally means 3x minus 1 times 3x minus 1. You have to FOIL that out. You can't just square the first term and square the last term, or you'll notice you'll be missing this middle term. So again, I have a quadratic. Let's move it all over to one side, set equal to 0. So I'm going to subtract the x from both sides, and I'm going to subtract the 3 from both sides. And again, factor completing the square quadratic formula. So I factored and set each of my factors equal to 0. So here we can subtract 2 and divide by 9, and here we can add 1. And again, I want to check for extraneous roots. And again, you'll notice that when I plug back in, one of my solutions worked and one of them did not. Now, something that might make this a little bit easier to spot, you cannot take the square root, a positive square root, and it equal a negative value. So as soon as you recognize that negative value there, that's going to be a shortcut to letting you know that's an extraneous root. Similarly here, as soon as I realized that this was going to be the primary positive square root equal to a negative value, I know I'm going to have a problem there.